So it's time now to move on to the driver and finals. Like I said, I was going to do the driver in the last video, but it was getting a little long. So we'll do the driver and the finals. What we'll do is, so here's the driver here. This transistor here, 2N2222, takes the output from the quadrature sampling encoder, further amplifies it, passes it through this transformer. And then we have these two BS170s configured in push-pull. We've built bias circuitry before, which sets the bias for the BS170s. So what we'll be able to do is put this part of the circuit together and then check to make sure that we're getting an appropriate signal around here and here. And then we can put the BS170s in, the final transformer here. There's a RFC that connects to 12 volts up here, a couple of capacitors, and then we're done and we'll be on to testing. So on the board itself, let me just get the light out of the way here. Part of the circuit that we'll be working on is the two BS170s go here, and then we put a heat sink over the top of it. The 2N2222 goes here, and then here's the two resistors which set the bias point for this transistor. And then there's a couple of transformers. One goes here, one goes around about here, and we'll shortly be done. So I'll get on with building up the driver, and then we'll come back and do some testing. So I'm about to put the bifiller winding through T3. I thought it might be interesting to at least show how I do it. Here's my kind of bifiller wound wire here, again with using a couple of screwdrivers, one and a clamp, and then you twist the other one. So that part's easy. So the next step is to wind the three. I've already wound the 6 windings here through, and now I need to wind the 3 windings. 3 bifiller windings through. And the way you know which way to start, because these leads need to come out of both sides of the same side of the binocular core, is if there is an odd number of turns, you want to start with the 2 leads on the same side. If there's an even number of turns, you want to start with the 2 leads on the other side. So we have a 6-turn, 3-turn, so I want to start the 3 turns in this side of the core. And this is where it kind of gets a bit tricky, because you don't have much room in these cores. So the advice is to use something sharp but not metallic, so that you can push the windings in, so that you can actually get this through. So it's a bit fiddly, a bit tricky, but we should be able to get this through here. So let me get this through. Again, starting on the same side as the already wound line. So that's 1 turn. Now, going back to produce, sorry, I'm out of camera here a bit, going back to produce the first half of the 2nd turn. That's the first half of the 2nd turn done. And second half of the 2nd turn. Push that through. The other thing that can happen with these cores is the cores themselves can be somewhat abrasive, so you'll end up removing the enamel. So you got to check, and that's why you kind of check continuity to make sure you don't have any of that happening. So this is the final and third and final pass through for the 3 turns. And there goes one side. And then here goes the other side. Oops. Yeah, that last turn is, there's not much space left there. So let me just see if I can push this down. And if you look closely on here, you can see that some of the enamel has indeed come off right here. So I'll have to check. I'll have to check continuity later on. I might have to rewind this one. We'll see. So I'm not giving up at this stage. So here's the final, the third winding through, and there's the finished product. So there's the 2 secondaries. The single primary, I'll do the same trick as before where I'll cut the primary a little bit longer than the secondary so it's easy to identify which is which. So anyway, that's that binocular core transformer wound. So like before, I've separated and stripped the enamel off the wires. So the 2 sides are here, and here, and here, and here. So I've left the primaries leads long, so that's easy to identify them. So we should have continuity across these guys, which we do. And now I've got to figure out which one here goes to which one of these 2. So let's probe here. Not that one. That one. Not that one, that one. So I'll swap those 2 guys over. And now this kind of lines up with the way the board goes. So I've got these 2 should have continuity, which they do. These 2 should not have continuity, nor should there be continuity here. And then these 2 should have continuity, which they do. So there's the primary, and that's one pair of secondaries, and this is the other pair of secondaries. So now we're going to install the binocular core that I just wound, the transformer T3, and that goes into this position right here. So just going through the connections. So these 2 are the single primary, and then these 2 are the secondary pairs. So I'll go ahead and get this installed. I will install these 2, I think they're 2.2 ohm resistors off camera. And then what we'll be able to do is do the INQ simulation that we did before and probe these points here to see what kind of signal we're getting. So let me just get the transformer installed. Let me try and keep my fingers out of the way here so you can see what's going on. So here's the two primaries go in here. And then each of these secondary pairs goes in the right slot. So let's put this side in. Here. Yeah, this one goes in here. This one goes in here. Push it through. And then finally, these 2 in here. So again, like the other ones, you've got to make sure that the primaries and the secondaries don't touch one another as you push it in. So let's just turn that over. Again, make sure you can see what's going on here. So if I pull that through. Okay. Turn it back over. As you can see, we're not quite right here. There we go, it's looking better. And back over. Need to pull these through a little bit tighter. Okay, that looks good. And make sure we're not touching anything here. No, that looks good. Okay. If you've accidentally got the secondaries touching, there's really no way of finding out once it's in circuit. So you got to check beforehand. Right. Let me solder this in. Check continuity. We're going to be able to check here and here. So that's good. So let me check actually here and here. Here and here. So that's good. Should be no continuity to the secondaries. And then there'll be continuity across all the secondaries. Okay, that's good. I'll install the two resistors which go here and here, and then we'll come back and do some testing. So just a quick update. I've installed the transformer and the resistors. Quick important note, they're not 2.2 ohm resistors, they're 220 ohm resistors. I made that mistake, put the 2.2 ohm resistors in, and it didn't work at all. So anyway, I don't think I damaged anything, but so anyway, what I'm doing now is probing right here, just to see the output. I'm simulating the INQ signals again, like I was doing in the last video. I've got AC coupling on there, so when I turn the push-to-talk function in the test, you can see there, we are getting a signal out, and if I zoom in, you can see that that is at 7.0520 megahertz, or the upper sideband, and the peak, we're getting a peak-to-peak signal of around about 4.8 volts. So there we go. There is it in, on, off. We'll do the same test again. I'll adjust the phase of the of channel 2 in my signal generator to 90 degrees instead of 270. And when we click on push to talk again, what you'll see is that the we're now getting the lower sideband, 7.048 megahertz. So that's just a quick update. Next step is to get the FETs installed, and then there's another transformer to wind, another RFC coil to wind, both with the binocular cores, and we'll go from there. So next part, I'm going to install the two remaining BS 170 FETs that go here and here. Now these parts are static sensitive, and I have to do the same thing that I did with the other FET, which is to say I have to bend the legs over. So I'm going to do that right now. Just got to get my pliers. So around about 4 millimeters from the end is where I want to bend it. And then install it. So again, the BS 170s are facing upwards. So let's see, that's about right for that guy. We turn it over, solder it in. Make sure you can see this. Lost my solder, there it is. with the other side. Yep. Excuse my hands in the way here. It's a little tough. Now again, you got to make sure that this spot right here is clear and free for the nut to go through. Okay, looks good. So all three. Now I won't put the heatsink on right now. It'll be good for testing if I have to replace one of the BS170s. It'll be easier without the heatsink there. So I'll get on and install the two resistors, and then we've got to wind this transformer right here, which is very similar to this transformer here. The difference being this is a 3-turn bifilar, 6-turn primary. This one is a 3-turn bifilar, 5-turn primary. So I'll get on with that. We'll speed through that, and then we'll install the RFC, which goes here. This one's a simple one. It's just a binocular core with a couple of turns on it. There's an electrolytic capacitor here. And then we're pretty much done with the kit, and we'll be able to test the output. So I've wound the T4. I didn't film it because it's the process of identifying the primaries and secondaries is exactly the same. So on the board itself, we have just the opposite of this one, in that these two are the secondaries, and this single one's the primary. And you can see that the primary goes off to the low-pass filter here with through this track here, and then the inputs to the secondaries are from the FETs. So you can see the track going from here to here, the track going from here to here. So it's kind of pretty easy to identify which is which in this one. So like before, we'll install it and then check it. So let's get the single primary in first. Alright, there's my tweezers gone again, forever losing my tweezers. Bear with me while I look for my tweezers. They're here somewhere. Aha, found them. Hiding again. So let's get the first of the secondaries in on this side. Similarly on the other side. I don't know if you can. Sorry, my hand's in the way there. And then the remaining secondary in here. And this side here. Push them through. Turn the board over. This is going to be a bit tricky to see. There we go. Then I've just got to pull these wires through from the other side. Let's go back and examine the other side. Now we've got a ways to go here. And what's going on with this one? Having trouble getting these last two in. There we go. Again, I'll make sure that the secondaries aren't in any way touching with the primary. There we go, that looks good. And now on to soldering. Good thing about these 30 gauge enameled wire is it's very quick to solder. Okay, that's that done. I'm just checking continuity here. So I should have continuity across here. And none to any of the secondaries. And then all of the secondaries will actually be connected as with the other transformer. So that's that done. I'll get on with the RFC, and then we'll come back and do some testing. So this is the RFC core wound. It's actually with 4 turns, not a couple as I mentioned before. Unlike the other other binocular cores, this is wound with the green number 26 wire that comes in the kit. So that RFC goes right here on the board, and just pop that down, hold it in place, turn it over. Let's get the camera on this. So there's the wires there. All right. Let's just test continuity on that. Yep. All right. And cut those off. And then as you can see on the back here, there's a couple of SMD components remaining to a couple of 0.1 microfarad capacitors, I believe. So I'll get those installed and then we can come back and test. So I actually filmed putting the 2 heat sinks on, but we had a bit of a disaster in the filming. So unfortunately, I don't really want to go through that again. But in any case, there's 2 heat sinks in the kit. One goes over the 2N2222 transistor, and you do have to install this after everything's put in place. Otherwise, you can't get to the components underneath it. So you install that, and then the other component, the other heatsink you need to install is this TO220 heatsink here, which goes over the top of the, having a bit of trouble with focus here, but it goes over the top of the BS170 FETs. So you can see here the kind of structure. Let me just pan back a bit so I can get a bit of focus here. So at the bottom we have the BS170s, and then to attach the heatsink you've got a I can't really see it in focus here, but you've got a screw that comes through the bottom. And then the order of the components is, there's the BS170, there's an SIL pad, there's the heatsink itself, and then on top of the heatsink there's a star washer, then the nut, and then you screw the whole lot together. So it's a bit fiddly, but it's pretty straightforward. So now we've got the 2 heatsinks on, I can do some testing of the output of this radio, and we'll see where we go from there. Okay, so this is the big moment. Obviously, I've tested it before we got on camera, but anyway, I thought I'd show you the big moment where we've got it hooked up as before, where we're simulating INQ using the signal generator. So you can see here I've got basically a 2 kilohertz signal coming out of channel 1 and 2 at 0.3 of a volt on each channel. And channel 2 is phase offset 90 degrees to channel 1. just on the test setup on the board itself, just to walk through some of the things. So I've actually got a dummy load on here, a 50 ohm dummy load on here, just to protect the finals. Obviously this is where the power comes in. Here's where the simulated INQ signals come in. This is the USB connection to the computer. And then I'm probing at the antenna output right here and sending that over to the scope. So let's just pan up to the scope and zoom in a bit on the scope so we can see what's going on there. So on the computer, I have actually got it tuned to 14.15 megahertz. So I should get with that 2 kilohertz signal, I should get either the upper or lower sidebands depending on which way the channel 1 and channel 2 attach the circuit. So let's go ahead and test that. Clicking on PTT, so you can see I'm getting a signal there. The frequency of the signal is 14.1480 megahertz, so that's the lower sideband, and that's coming through at a peak-to-peak of 2.6 volts. Now, the actual output power depends almost entirely on the amplitude of the I and the Q audio signals coming in. So as you ramp that amplitude up, so does the output power. So let me go ahead and do that just to demonstrate that. If I go to amplitude here, let me increase that to say 0.7 of a volt. Now obviously I have to do that on both channels, otherwise I'll get a mismatch between the two. So when we go to 0.7 of a volt, you can now see that we are at 6.08 volts peak to peak on the output there. Now the actual output coming through is around about 2 volts. So let's simulate that on channel 1 and channel 2. Oops, I've just turned channel 1 off. Let me go to channel 2. Again, go up to 2 volts. There we go. So that's 2 volts coming in on the audio signal. You can see there we're going off the scale there. When I rescale that, I'm getting around about 18.4 volts peak to peak, which is a little less than 1 watt output power, and that's on the 20 meter band. So let me go back to around 0.3 of a volt, and then we'll move over to the spectrum analyzer, and we'll have a look at what's going on there. So that goes back to 0.3 of a volt. Let me turn the spectrum analyzer on. Bear with me, let's just confirm that that's working again. Boom. Okay, so there we have the signal coming through. Let me take the probe from here. And so this is low enough level of a signal. I've got it going through a 20 dB attenuator to the spectrum analyzer, so I don't expect this isn't going to be a problem for it. So let's pan over to the spectrum analyzer now, and we can see the output. I've got to adjust the stop and the start frequency. So let's pick 14.1 megahertz as a start frequency, and let's say go to 14.2 megahertz as the stop frequency. So let me just check that one more time. So now so there you can see the signal. There's other stuff going on there. So what I'll do is I'll zoom into that signal, and we'll see what exactly is going on there. So let me increase the start frequency, decrease the stop frequency, and we should see some interesting stuff going on in the signal there. So again, not quite enough. Let me decrease that again, get a bit more resolution going here. Increase this guy. And let's change the resolution bandwidth down to 100 Hertz so we can get some nice signals there. And so you can see there, let me turn the marker on so we can actually see those signals there. So there is the 15.15 megahertz signal in the middle there. That's kind of the leftovers from the oscillator, which is running at that. And then you can see there, I've got a big signal on the lower sideband around 14.148. So there's the lower sideband. But you can also see we haven't completely suppressed the image here. So we've got an image there. Now it is down 30 dBs, nearly 40 dBs. So that's a good thing, that it's down that it's down that far. But let me just play around. So let me adjust the phase offset, and you can see if you get the phase offset wrong on these IQ radios, see how that lower sideband, the upper sideband starts to come into the picture there. So this is all about and there are facilities within the SDR software to balance that I and the Q signal so that you get that the other sideband as suppressed as possible. So again, let's change the phase offset. Let's go to 270 degrees, and you should now see that the upper sideband is the signal that is now present. So here we go up to, and there it is at 14.152 megahertz. So we've tested the lower sideband, the upper sideband. The purity of the signal seems pretty good. I mean, these are both well down. So we don't, there are, if you actually, let me just adjust the amplitude here. Change that up. Oops, wrong way. If I decrease the attenuator, you can see there's actually more stuff going on here. So we've got other harmonics that aren't being completely suppressed. So we've got, here's the center signal, here's the upper sideband, so this is prominent. Everything else is down greater than 30 dB, which is good. But then we've got other signals here, other harmonics, and each one of these harmonics is exactly the input audio frequency apart. So let me change that to, let's go to 1 kilohertz on channel 1 and channel 2. And you can see there now each one of these harmonics is 1 kilohertz apart. So anyway, interesting stuff. At this point, that's kind of the build pretty much done. Obviously, I've got to, the final test is obviously to get it on HDSDR and confirm that it's actually working. But we're all working from, I guess, a measurement perspective, a theoretical perspective. So I guess the ultimate test is if we can actually transmit and get someone to receive us. So that will be the next step. There is some stuff in HDSDR that we'll have to do. I'll probably do a follow-up video of that, but at this point, we're going to put a stop, and I'll get back to you later.